So wherever it is that you get a calculus class, all calculus courses are basically set up with the same kind of a layout. Chapter 1's an algebra review, because calculus is a lot like an algebra 3 sort of course. It's just a lot of algebra in it. Chapter 2, you get your first actual calculus topic, which is a thing called limits. Limits are at the foundation of everything that we do all year, but they sort of will fade to the background after being a chapter in the foreground, and they just sort of will work silently and invisibly behind the scenes for most of the year, with an occasional time to poke their head out of their cave. Chapter 3 is about a thing called derivatives. We'll get into that another day when we get to chapter 3, but derivatives are based on limits. So I'm just going to read some stuff off of page 63. If you want to join me on page 63, I'll just sort of read some stuff that they wrote in the book that kind of cues you up for the chapter. I'm going to go bottom of page, no, I'll go top of page 63. I'll just start where they started their typing. So 2.1, limits of function values. They say a tennis ball falling from the Empire State Building is going to accelerate at first, but after 4 or 5 seconds it reaches a limiting speed called the terminal speed. The ball can continue on this speed for the remaining time in the air. A falling leaf is going to reach its terminal speed more quickly than the ball does, a falling feather more quickly still. In each case, the resistance of the surrounding air imposes a limit, word of the day is limit, on how fast the object can fall. Another paragraph. When you cough, your windpipe is going to contract to increase the speed of the air going out. Naturally, there's a limit to how fast the air could go. If you contract your windpipe a bit, the air speeds up, but if you contract it too much, the air gets choked off. There's like a sweet spot there. When a new species is introduced into a region, its population grows rapidly at first, but then begins to level off as members encounter predators and restrictions on food and space. As the days pass, the population, growing ever more slowly, approaches a limiting size called the carrying capacity of the environment. You probably encountered that a few years ago. You probably remember the emergence of the stink bug. Like it got to North America, and the stink bug just like took over the world for a while. They were everywhere. But it hit a limit, and things leveled off. These and many other examples convince us that we live in a world of limits, and this is where calculus comes in. Most of the limits that interest us can be viewed as numerical limits to values of functions, formulas, equations, and calculus is the right math for finding the limiting values of functions. I'll skip over to the left, where they say we live in a world of limits. It says there's a limit to how far a cannon can fire a shell. There's a limit to how much an investment can earn in a year. There's a limit to how fast we can stop for a red light. There's a limit to how much weight we can lift and to how long a battery will last. The list is nearly endless. That's kind of the concept of some of what's going on in this chapter. Just there's limits to things. I'm going to take a small walk. I think in trig once we had this little conversation, and I told you we'd get into this in calculus. Sometimes it does come up in trig. If I wanted to walk toward my cabinet and I wanted to cut the distance in half with each move. So I'm going to take a move here and I cut the distance in half. I take another move, I cut the distance in half. I continue to cut the distance in half. I continue to cut the distance in half. Continue. Will I ever touch the cabinet? Probably no. But at some point, I'm going to be so close to that cabinet, you can't even tell the difference. So where I stopped walking, you could tell the difference because I had like an inch left. If I had kept going and going and going, eventually I would have been so close, you might have had to approach me and like see if you could slide a paper between my nose and the cabinet and see if it would fit, and it would. Could I get closer than the width of a piece of paper? Eventually, yeah. If I kept cutting it half and half and half, eventually you might be like, maybe he's touching it, I can't fit my paper through there. Or maybe you can shine a light through there. And I would say like, oh, there's a crevice, we can shine light through it. I technically actually could maybe get so close you couldn't even shine light through it. But still not touch it. Okay? At some point you're so close that for anything that's even measurable, you might as well be touching it because you can't even measure what's left anymore. That's a little bit the idea of limits. The idea of limits is You're getting closer to a destination. Do you actually arrive at the destination? Sometimes it's a matter of this. I don't know. Like, I'm awful close. Did I actually get there? I don't know. Maybe I did, maybe I didn't. Okay. Here's a math question to kind of break the ice as well. And I think the first little bit of the homework will have you take on a math question like this. If I give you a function value, or a function, give you a formula, an equation, and I ask you to plug into this, for most numbers, you can plug into this just fine. But if I ask you to plug in 2, things go haywire. If you tried to plug in 2, the top would become 0. The bottom would become 0. And then for many centuries of math, civil war could break out over arguing how that should go. Can you think of something you could argue about? 0 dividing 0. Can you think of something that would be a valid argument?
Impossible.
You could argue that it's impossible. Why can you argue it's impossible?
0 on the bottom.
You're not supposed to have zeros on the bottom. What else could you argue for?
0.
You could argue for 0, because traditionally 0 dividing other things is 0. What else could you argue for? 1, because stuff dividing itself is 1. This answer is actually, best answer is not going to be any of those 3, okay? But civil war could break out over those. Up to this point, we always just said like, we can't do it, give up. What they're going to do with these limits is basically create a concept of 2 itself is a trouble zone. We've got civil war breaking out. So let's not worry about 2. Let's worry about just trying to get really close to 2. Because if we try to plug in 2, things blow up. Can you pick a number that's close to 2 that maybe we can help give us a guesstimate?
1.9.
1.9 would be good. If you plug in 1.9, out is going to come. You don't have to do the punching, I've already pre-punched these. 2.9256. And that gives you some idea. Can you pick something better than 1.9?
1.99.
1.99 gives you 2.9925. Did you do better than 1.99?
1.999.
1.999. That'll give you 2.99925. At which point you probably get the sense that when you get super close to 2, the result is expected to get super close to 3. Now, I didn't punch it in, but I bet if we went 1.9999, this probably starts off 2.9999. You know, it's getting super close. So in this case, 0 divided by 0 potentially is like 3. Another thing you could have yelled that would have been as equally good would have been to yell 2.1. 2.1 is close to 2. 2.1 would give you 3.076. Better than 2.1 is 2.01. That would give us 3.0075. Better than that is 2.001. That could give you a 3.00075. At which point you get the same sense. When these get super close to 2, the results are getting super close to 3. That's the idea of limit. Possibly another tool in our toolbox, other than plug-in numbers that we've used to do answers to mysterious questions in our past, is to just graph stuff. You don't have to graph it on your calculator. I graphed it on mine and just made a graph. This graph is pretty wacky. It's got like a branch going this way. It has a vertical asymptote at -2. Because if you plug in -2, that also gets you 0 on the bottom, causes some issues. And then there's a branch that's going through the right, but the branch that goes through the right is weird because it looks like a U-ish kind of thing. But if you go over 2, there's a hole in the graph that would sort of line up with over 2, up 3. The graph is trying to touch that point, but it can't. The calculator grapher can't plug in and do that, and it creates like a little hole in the graph. But we can still read from this, if we find an x of 2, where does the graph seem to be wanting to go? It wants to go to 3, it's just, it can't. Like when x is 2, y wants to be 3, and it just, things blow up when you try to plug in. That's also like an idea where limits come into play. Question about that? Does that make sense? So I'm going to take a walk to my left and we'll introduce you to some punctuation and symbols and math.
How far left? Are we going like full way to the?
All the way.
Okay. We're good.
So what we just discovered over there was when x was approaching 2, that f of x, that y, was approaching 3. So here's some symbols that we can use to just communicate that idea. There's a thing called the right-hand limit. When we're doing the right-hand limits, what we're doing is we're picking some numbers that are more than what we wanted. So when we were looking at 2, when I was playing games with 2.01, 2.001, 2.001s, the stuff that was more than 2s, we were computing right-hand limits. So the way we can communicate that is the limit, as x approaches 2 from the right, f of x was just the name of the equation, we got 3s. When we reply, this doesn't mean things are positive, this is just a symbol that means it's more than 2. This is our 2.01 kind of frame. So when x gets really close to 2, but is a little more, we kept basically getting 3s. There's also a thing called the left-hand limit. For the left-hand limit, that would just be anytime we plugged in things that were less. So when we were doing our 1.99s and 1.999s, we were doing left-hand limits. The left-hand limit, we go limit as x approaches 2 from the left. This little minus doesn't mean that the 2 is negative, it's a positive 2. If I wanted a negative 2, I'd put a negative there as I historically would. This means I'm approaching 2, but from the left side of it, function had whatever name it had, that was also 3. Sometimes those agree. Sometimes those can disagree with each other. You can get different answers for the left hand than you do for the right hand. Look who it is, live in person. We're filming you a video. Here you are. All right. There's also a thing called a two-sided limit. The two-sided limit happens whenever those agree with each other. So in this case, we do have a two-sided limit because the limit from the left was a match for the limit from the right. Both agreed with 3, so our answer is a 3. Question about that.
Is the two-sided thing always going to be the same as the other two things?
If they match each other, then this will be the same as its friends. If these mismatch each other, then that is an impossible no, you go with our no answer sort of thing. So if from the right we have 3, but from the left we have 7, the two-sided one, we just say we can't do it. What's that? Sure. Let's take a brief time out. We'll resume once she's a little more settled. Okay, so
We're good.
So we're running again. The first part of the homework is going to be, they'll have you create a little table like we did, just putting in stuff with 0.9s and 0.99s and 0.999s and stuff like that. The second bunch of homework, I'm pretty sure, is going to ask you to find limits by using function values, or maybe they'll start by using graphs. I'm not sure. We'll do them both, but the easier thing to do is to find limits from functions. And so if they ask you to try to find some limits from functions, the first thing you would try to do is just plug in. If you get an answer, good, you're done. If you get a fraction with a 0 on the bottom, we're going to have to try to do something else, and we'll see if one of you can come up with that idea in just a second. So if I ask you to do the limit as x approaches 4 of x plus 3, just plug the 4 in. 4 plus 3 makes 7. That's all you need to do math-wise. That should be some pretty easy money. And what's really going on is this isn't truly 4. You know, what this truly is 3.999999999, or 4.0000001. But if you stay super close to 4, one side or the other, and add 3 to it, you might as well end up at 7. Like that's where you are. You're so close to 7 you couldn't tell the difference. So likewise on this, if x is like super close to 6, you might as well just plug the 6 in and see what happens. On this one, out would shoot 40. Question about that? If I decided to go back and do this to this problem, that changes nothing. Okay, if I put the little minus, that would just mean I'm like a 3.9999999 kind of number, but you still might as well just plug in the 4. If I do a little plus there, all that means is I'm thinking about 6.0000001. You might as well just plug in 6. Okay, so if you're plugging these numbers in, it doesn't really matter if they do a right hand, a left hand, or a two-sided. It's all about the same. This one, if you try to plug in, I would always try to plug in the bottom first, just because that's usually a quicker place to plug. If you try to put 1 into this, it makes the bottom 0. It would also make the top 0, but I'd focus more on the bottom. If the bottom's 0, you have an issue you'd probably rather resolve. Either you have a suggestion on what you could try to do to resolve that issue, you're trying to plug in and the bottom is 0 and things are messed up.
Get super close to the 1.
We could. You could go ahead and build the same kind of table again. That'll be harder than what I'll suggest. An algebra idea from days gone by, algebra 1, algebra 2 skills.
Factor.
Yeah, look to factor, because factoring might allow you to cancel. So if we can factor cancel, I would look to do that. I would try to plug in first just in case. Like if this was an x plus 1, just plug in, see what you get. But if you're plugging in and the bottom 0, that's where I would look to go factor cancel. So the bottom is like it's in parentheses already invisibly. How's the top going to go?
X minus 1, x minus 1.
X minus 1, x minus 1. You do get a nice cancel. You plug 1 into whoever's left standing, and out comes 0. So in this case, 0 divided by 0 was 0. Sometimes that happens. Sometimes it's 3. Sometimes it's anything. You just don't know until you get there. Similarly, plug in -2, it makes the bottom 0, so you know there's some kind of an issue. Maybe you can resolve it with a factor cancel. So factor plus 4 plus 2. Get a little cancel going. Plug -2 into who's left standing, and out comes 2. 0 divided by 0, in this case, 2. Does that make any sense? No. Okay, but that is truly the best answer, and that was why they had a lot of trouble in history of this problem coming to any kind of agreement, because some zany things happen. 0 divided by 0 seems like it should be 0, 1, or impossible. It doesn't seem like it should be 2, but sometimes it is. Question about that part of the world.
Is that like not an illegal thing to do in math, or is it just for the lesson that we're doing that? Like factoring instead of getting 0 on the bottom?
0 on the bottom is always bad news. So if my instructions to you in an algebra world was plug in -2, you can't do it. It's impossible. So I'm not saying that plugging -2 into this does create 2, because it doesn't. It's still impossible to us. But if we had to have a best answer of what's going on in that area, close to that point, when you get close to -2, you might as well land on 2, because that's where you are. You know, can you actually land on -2? No. But if you could, what would happen? In this case, you'd get 2. Okay, but this isn't trying to really answer the question of what's happening exactly at -2. It's just trying to answer the question, what happens when you're really close to -2 on one side or the other? It can answer that question. But there is not now, nor will there ever be, a way to take -2 and truly plug it into that and truly have an answer at that exact spot. But if you can have an answer for -1.99999999999 in almost all circumstances, you're close enough. Does that make sense? Does that answer your question?
Sort of, yeah.
Sort of. Question from that world? The second thing you're doing is working some graphs. So I have a ridiculous graph I copied and gave you. You probably need one. I emailed you a PDF of it, but then you're here in person. Tricky. So this is a far more ridiculous graph than your homework does. What your homework is going to do is a selection, and yours is over here to your right. Your homework will do a selection of like mini graphs on this, and it'll ask you to do one of two things. One thing it's going to ask you to do is on a graph to find a function value. Okay, to find a function value, what you're going to look for is just some filled in dots. And I'm going to do all of the function values first, because that's a little bit usually easier for people to understand. So when I'm talking about filled in dots, I'm talking about this is a thing that we're including. I'm not talking about this. Okay, there's a hole in the graph. There's nothing filled in there. That's a gap. I would be talking about other dots that I didn't explicitly fill in. But there is a dot right there. I didn't fill in dots all along this curve, but this continuous piece of curve has an infinite amount of points that comprise it. So there is a dot up there, even though I didn't make one. I am talking about this. I am talking about this. I'm not talking about these holes. So what we're looking to find is a filled in dot. In the homework, on a test, on a quiz, on the worksheet that I gave you, everything I'm providing you is an x-axis address. So if I ask you to find f of 0 or f of 1, okay, for f of 0, I'm asking you to go over 0, and all answers you give me are going to be y-axis numbers. I will give you all x-axis addresses, you'll give me all y-axis results. So if I tell you to go 0 on the x-axis, how high are you when you find me a filled in dot? 1. So you could put that on that little grid thing, that's that first column, top 1, I think was for function value of 0, right? Is that how it's laid out? So f of 0 would be 1. F of 1, you go over 1, find your filled in dot, how high are you? 4. F of 2 is a tricky one. Why is f of 2 a tricky one? Can't do it. So that just use the impossible symbol for f of 2. F of 3. If I could draw, I'm a little bit skewed on the board. I think my paper graph is better. Wait, I misdrew something. Sorry. When I went on the board, this was actually over there. So correction to board graph. Correction to the 2 answer. Sorry about that. If you follow your paper graph, lined up with 2, how high are you? 6. How about lined up with 3? 4, roughly. Track up. Roughly, that lines up with 4. I didn't explicitly fill that dot in, but the curve is made up of a bunch of filled in dots. At 4,
Can't do it.
that's the one we can't do. At 5, all the way up to 6. At 6, can't do it. So that little first column sequence ran 1, 4, 6, 4, impossible, 6, impossible. Question about that.
Is this the idea that's usually on like the SATs every once in a while?
I don't think this would ever appear on the SAT, but they will. You know what? I take that back. The f of 1's, yeah, that does appear every once in a while on the SAT. Yeah, f of 1 is like on a graph, go over 1, see how high it is. We have seen those problems. Yeah, limits don't make the SATs, but the f ups, yeah, those make. Question about that. Okay, the second column, I'm trying to do left-hand limits. So if we try to do limits, what we're looking to do is come from the left side on this column, and we want to get super close to the location that I specified. I'll just tell you the answer to the first one is impossible, because I can't do the limit from the left into the beginning. There was nothing there. That would be stupid. Okay, so we can't do the limit from the left ever into the beginning. So start off that one with an impossible. But at 1, what you're trying to do is imagine you're like a spider walking on this graph. You're coming in from the left. You have an ability to keep track of what you're lined up with. As you're the spider walking on the graph from the left, and you get close to lining up with 1, how high are you? We're the spider walking in until we line up with the chalk. How high do we feel like we are? 4. Okay, that's in agreement with what we did a second ago when we got to 4. Sometimes these answers agree, sometimes they don't. When we try to get to 2, we're still a little spider. We're walking from the left. We're going to walk from the left until we're super close to lining up with this. If we're walking in from the left, how high does that spider feel like he's going to be when he lines up with 2? 1. And that time it's in disagreement with where the dot was. Because the spider walking from the left is really only aware of the hill that he's on. He's 1 high. He has no idea there's like another road up there. It's just not a thing. For the spider trying to walk in, continuing our path to the left, I guess he's a magic spider, so he made a big hop, I guess. But now he's walking in from the left until it lines up with 3. How high is the spider? 4. Which agreed with what we had a second ago. I mean, that doesn't have a name, it's a coincidence. It keeps on walking in from the left until it's lined up with 4. How high is that going to be? Basically 0. Because the spider's not worried about landing in the hole. The spider's just worried about getting super close. The spider, when we're doing the limit at 4, the spider's thinking 3.99. How high am I? Basically 0. Spider walks some more, coming in from the left, walking in to line up with 5. That height would be 2. Walking in from the left, zooming in on 6. How high that is 3. So that column goes impossible, 4, 1, 4, 0, 2, 3. Anything about that that needs a little more illumination? The next column, we're coming from the right. So if we come from the right, let's go backward because we're coming from the right. So if we come from the right into 6, what do you think there?
Impossible.
That's impossible. Just like we can't come from the left into the beginning, that's stupid. Coming from the right into the end, that's also stupid. So that's impossible at 6. So bottom answer is 6. Spider walks from the right. How high? 4. So working up the column, we got a 4. From the right into the 4 is 0. From the right into the 3, 4. From the right into the 2, 6. From the right into the 1, 0, or is 4, sorry. And then from the right into the 1, or into the 0, is 1. So So reading down that column, I'm gonna go 1, 4, 6, 4, 0, wait, yeah, 1, 4, 6, 4, 0, 4 impossible. Anybody about the rights? Okay, for the lefts, the easiest way to do the lefts is just look at the, or the two-sideds, take that back. The easiest way to do the two-sideds, which is the last column, is look at the answers you just made. For it to be two-sided, there has to be an agreement. So, based on the number 1, the second line down, what we had is, we're not looking at the function values, okay, but we're looking on limit left and limit right, these middle two columns. If the middle two columns agree, we have an answer. If the middle two columns disagree, we do not have an answer. So the line for 1, we've got 4 versus 4. So the two-sided limit is 4. Where else is there going to be a two-sided limit then? At 3, the answer would be 4. At 4, the answer would be 0. At 2, it would be impossible because 1 disagreed with 6. So at 2, we're going to go impossible. At 5, 2 in competition with 4, we're going to go impossible. The beginning and ends, though, we're going to treat as a special case in just a second. For the beginnings and ends, it isn't really a fair contest because the left didn't even have a chance. So if we are at the very beginning, special exception for the very beginning of a graph is if one of the sides can't exist, just go with the other side. Let the other side have its way. So that first one where we had impossible versus 1, just go with 1. That wasn't fair. And likewise at 6, it's not really even fair. If it's 3 versus 1, we couldn't even do it. Just go with 3. Okay, so that last column goes 1, 4, impossible, 4, 0, impossible, and 3. And then I'll explain one more little bit of stuff, looking at the graph, not at the numbers, but any question about what we just did? I'll make this hand gesture at you the next couple of weeks, many times. Two-sided limits existing means the graph's going like this, and it like meets somewhere. Now where I'm meeting, there might be a hole or there might be a dot, I don't even care. But if the spider is like going to the same spot because it's going like this, we're good. Where the limit doesn't exist, to quote Mean Girls for the first time, is when we have this kind of thing. You've got a high road, you've got a low road, and they're not the same road. The spider is going to 2 different heights. So like at 1, the two-sided limit existed because from the right and left, there's an agreement that we're lined up 4 high. And we happen to hit a dot, but we don't care if it's a dot or a hole. Something like this location. From the left and from the right, we're touching. There happens to be a hole. We don't care that there's a hole. We just care that the spider from the left and the spider from the right, they're headed to the same basic location. That's why those two-sided limits existed for 1 and 4 is there's agreement. At 5, there wasn't, because we've got like high road, low road. You know, the spider from the right was up high, the spider from the left is down low. When it's disjointed like that, that's limit does not exist. Likewise here. When we go low here, we go high there, there's a disjointedness. Anytime there's a disconnection to the graph, the limit does not exist. I think Lindsay Lohan says, like, if the limit doesn't approach anything in particular, then the limit does not exist, and they win the contest.
They win the game show. The game show.
But this, yeah, on the game show. So this is no good, no, can't do it. An agreement is good news. Back to a geo question from a second ago. This crazy graph, we looked at 2. The two-sided limit existed. The spider from the left and the spider from the right, as we zoom in on 2, they'd be going to the same height. When we plugged in numbers less and plugged in numbers more than 2, there was an agreement. It was basically 3. Okay, that's a two-sided limit that existed. At -2, the two-sided limit does not exist. Because if we zoomed in on -2, which would also blow this equation up, you know, a spider walking from the right is headed like to infinity. And the spider headed from the left is headed to negative infinity. Those spiders could not be farther away. Okay, the right-hand limit is infinite. The left-hand limit is negative infinite. two-sided? No, you just can't do it. There's too much of a disagreement. That's an impossible question. I think tomorrow is limits involving infinity, and it's actually the graph that she had to look around here and Samuel to see in the movie. Question about limits. Let's take a brief homework look. Might as well just record this too, unless you already had it. Where we're headed, homework, he stopped at 72. Syllabus would know the problems. For the first two, you're building like a little table like this, and you should notice an agreement among all the answers that you're getting. Then they do graphs first. From 5 to 16, they do a bunch of mini graphs that are like a subset of my ridiculous graph. So they might just do like one mountain, or one disjointed pair, or they'll do a mini version of these graphs from 5 to 16. Starting on 23, you're looking to just plug stuff in. So from 23 to the end, it's just plug in city, a little bit of back and forth.